Guys, so welcome to the last lecture of experimental techniques. So in this lecture we'll be talking about a number of things. First of all, solubility of gases, the nature of gases, the density of gases, the drying agents we use, the methods of collection. There are four actually. uh, then I have to talk something about thermal decomposition and metal plus acid reaction, although we'll be doing them in acid basis salts and metals chapter that is actually upcoming. But I'll actually talk about the collection of gases part here. So this whole of the lecture is based on collection of gases. So first of all, let's move on to the first part, that is the solubility of gases. All right, so here's a table that you need to memorize or you need to make a sense of. First of all, you need to know the soluble gases. So nitrogen dioxide, chlorine, it's hydrochloric acid if it's dissolved in water, but you call it hydrogen chloride gas otherwise. All right, so it's hydrogen chloride in this state, and sulfur dioxide, sulfur trioxide, ammonia, and hydrogen iodide gas. All of these are soluble gases. And of course, oxygen, nitrogen monoxide, carbon monoxide, and hydrogen are insoluble gases. Out of these gases, I would recommend you to at least remember hydrogen very thoroughly. We test hydrogen a lot. All right. Now there's an exception that carbon dioxide is partially soluble. So the reason for telling you that it's partially soluble is because the collection over water isn't possible. All right, so there is a reason why I had to mention this, that carbon dioxide is partially soluble. It's because I need to tell you that collection over water for carbon dioxide is not possible, although I'll be restating it further along. All right. Next, next we have the acidity and basicity of a gas. All right. Now, some gases are acidic, some are neutral, and some are basic. As for basic gases, ammonia is the only basic gas found in nature. So it's the only basic gas found in nature. Although we have synthetic gases, but it's the only basic gas found in nature. All right. It's a key thing to remember in nature. And also, it's extremely soluble. Like, it's one of the most soluble gases out there. All right. So, yeah, that is for ammonia. Next, neutral gases. Methane is neutral, oxygen is neutral, hydrogen is neutral, nitrogen monoxide is neutral, and carbon monoxide is neutral. And acidic, sulfur dioxide is acidic, sulfur trioxide is acidic. uh, and these things have a lot of importance because when we'll be talking about the contacts process, you'll see their importance there. Nitrogen dioxide is also acidic, and this is also important because we actually talk about the greenhouse effects and the global warming and the acid rain. Now, nitrogen dioxide is actually responsible for acid rain if we talk about it, and as well as sulfur dioxide. Sulfur trioxide is not, primarily because it isn't formed on Earth. Like, we don't release sulfur dioxide. Sulfur dioxide moves into the upper atmosphere and oxidizes to form sulfur dioxide. Although all of this is what we'll talk about in the next chapters. Carbon dioxide is again acidic. Chlorine is also acidic, and hydrogen chloride gas is also acidic. All right. Now there's a key thing to remember, and it's that when I say acidic, what is actually its test? So if I expose these gases to, let's say, a damp litmus paper, a damp blue litmus paper for acidic gases, then it will turn red. It will turn red. All right, that's a key thing to remember. And basic gases, they turn damp red litmus paper to blue. And this specifically is a very important test for ammonia. It's the only test that you're allowed to write in your exams for ammonia. This this is actually a test for ammonia. So whenever we say that there's a gas that has turned red litmus paper, damp red litmus paper from red to blue, we're always talking about ammonia. There's no other gas in your syllabus that turns red litmus paper to blue. Alright, and there's also a key thing to remember is that chlorine bleaches litmus paper. Now, one more thing to remember is that chlorine also bleaches litmus solution. So, bleaches litmus solution as well. Here, alright. It bleaches litmus solution as well. There is a special property of chlorine that you need to remember. I'll be restating these facts throughout the syllabus. Alright, now let's move on to our third point, that is the density. Now, this is by far the easiest one. Alright, now when we talk about density, um, the only thing you need to remember is that we are comparing it to oxygen. Now, the molar mass of oxygen is 32 grams per mole. Alright, and what we actually do is that we take the molar mass of all of the gases and we compare it to oxygen. Although I agree that air is 71% nitrogen, but we actually take oxygen to be the relative mass of air. Alright, so anything we will talk about will be compared to air. And one more thing is that we will never talk about nitrogen. Nitrogen is never asked. And there is a reason for that. We won't ask you to compare 70% of air with 20% of air. Like, we are taking oxygen to be 20% of air and yet giving it so much importance that we are saying that we compare every gas's mass to oxygen. So we won't ask nitrogen because it actually comprises of 71% of the air. So yeah, we won't ask you about nitrogen. So here, for example, methane, it has 16 gram per mole of molar mass. So that's quite less than oxygen. So we say that it's lighter. It's lighter gas. Nitrogen has 28 gram per mole. It's again lighter. Chlorine, on the other hand, is 71 gram per mole, which is lot more than oxygen. Therefore, it's heavier. Same for sulfur dioxide and sulfur trioxide, and so on. You can compare any gas with oxygen and find out its density relative to air. Next, we move on to drying agents. Okay, so this is one of the most important topics you need to know. Alright, so drying agents. So when we collect gases, they're usually damp. Damp means they they have water content in them. We need to sometimes we ask you to have a pure dry sample. Now, when we're talking about dry, it cannot be damp, so we need some drying agents for that. We pass the gases through one of these four things, and the resultant gas would be a dried gas, a dried sample. So first drying agent is concentrated sulfuric acid. Now you need to know its state symbol. It's actually liquid. And now why do you need to know the state symbol? Because if it's a liquid, you're going to put the drying agent inside a flask. However, if it's a solid, you're going to put it inside a special apparatus drawn like this, right? Right? So, silica gel is also solid, anhydrous calcium chloride is solid, and anhydrous calcium oxide is also solid. Now, you need to know the nature. Whenever I'm talking about nature, I'm talking about either they're acidic or basic or neutral. So, they are for concentrated sulfuric acid, of course, it is acidic. Same for silica gel and calcium chloride actually. However, calcium oxide is basic. Now, I left the last column empty because I wanted to fill it with you guys. Alright, so think about it just for a moment. For example, I have ammonia and I pass it through ammonia, which is extremely basic gas, and I pass it through, let's say, concentrated sulfuric acid. Will I get a dry sample? The answer is no, because it will react. Ammonia being basic and concentrated sulfuric acid being acidic, they will react. So we can't use concentrated sulfuric acid. So what can we use a concentrated sulfuric acid for? For the collection of acidic or neutral gases. So acidic or neutral, either of the two. Same will be the case for silica gel and anhydrous calcium chloride. So acidic or neutral, not at all a basic gas. They will react. Now, as for anhydrous calcium oxide, it's basic. So I can never pass an acidic gas through it. It will again react. Alright, so it will be either basic or neutral. Alright, so these are few things you need to remember. Alright, next we move on to the methods of collection. So we have four methods of collection in our syllabus. They're upward delivery, downward delivery, gas syringe, and collection over water. So first of all, upward delivery. When I'm talking about upward delivery, it is only for lighter gases because lighter gases will move up, then they are lighter, so they'll move up than air, and they will displace it. So one thing that you need to remember is that the gas will be collected here, and it will displace the air from inside, and therefore we also call it downward displacement. So first of all, it's for lighter gases only. Then it can also be called downward displacement. Now the third point, we cannot do any measurement. Now some students might think that what if we use a calibrated measuring cylinder? Now just think for a moment. How will you be sure of where is the gas? Now I agree that lighter gases do rise up, but it's not like they can never go down. Some gas might also escape. So yeah, so that's not possible. So, we cannot do any measurements. So this is an inefficient process. So next is downward delivery as well as gas syringe. All right. So downward delivery. So downward delivery is for heavier gases, and of course you know that it will displace air upwards, so it's also called upward displacement. And again, we cannot do any measurements because some of the gas might also escape and we won't know the exact position of the gas in the beaker or the measuring cylinder. Now the third one is a gas syringe. It's the most effective method. It's the best actually. Why? Because you can do measurements, you can pass the gas through any sort of drying agent before it. It can collect any gas, soluble, insoluble, basic, neutral, any of the gas. So yeah, gas syringe is the most efficient method, and we will be using gas syringe in the further experiments that I'm going to show you. Next is collection over water. Now, why do we do collection over water? It is to remove insoluble impurities. Now, let's just say, remove soluble impurities, sorry. Let's just say that I have hydrogen gas plus sulfur dioxide and I have to collect hydrogen. It just says pure sample of hydrogen, not dry. So, what I can do is that I pass this through water and the sulfur dioxide will get dissolved while hydrogen being insoluble will pass. Now one very key thing to note is that in all of the apparatus I will draw, the tube that causes the gas to enter must be dipped inside the liquid. Why? Because the fluid needs to bubble through, the gas needs to bubble through the liquid. Alright? And similarly, it's either this apparatus, or this. You can use any of the two. We have no problem in that. It's just up to the situation. Now, in this apparatus, the second one, one better point is that you can do measurements of the gases. Of course, because um, you can note the volume of water that is displaced, and that could be measured quite accurately. Next is the thermal decomposition of metal. Now, of course, I'll be teaching you this reaction in the upcoming metals chapter, metals and non-metals chapter, and periodic table as well. But I need to mention a few things. Now, this is a very key reaction in our whole chemistry: thermal decomposition of nitrates. Now, whenever I actually thermally decompose nitrates, they form nitrogen dioxide and oxygen. Alright, not always. There are a few metals that form nitrogen dioxide and oxygen, but you don't need to worry. We'll be learning about them in the upcoming chapters. So, what I can do in the case of thermal decomposition of metals is either of the two. Either I use a boiling tube or a heating crucible. Alright, you need to remember the names, we ask you them in the examinations. Alright, when do I use a boiling tube? I use a boiling tube when I have to do decomposition as well as collection of gas. However, if I only need to do a decomposition, I will use a heating crucible. Right. So what I'll do is, when I'm talking about a boiling tube, so here as you can see is that I have a boiling tube in which I have the metal. Let's just say that this was the metal and I heated it. Now, some some of the metal nitrate actually decompose to give calcium oxide, nitrogen dioxide, and oxygen. And so, what I do is that I take a tube and insert it inside the boiling tube, and the gases move through the boiling tube into the beaker containing water. Now, why have I chosen water? Because nitrogen dioxide is soluble in water and it will dissolve, while oxygen is insoluble. It will not dissolve. Alright? Now, the oxygen being insoluble rises up, and nitrogen dioxide is dissolved actually. So, what will happen is that this oxygen moves through the other tube into the container, into the flask containing concentrated sulfuric acid. Now, there is a thing that we prefer using concentrated sulfuric acid over any other uh, drying agent. It's because it's liquid. It's the only liquid drying agent we have in our syllabus, and therefore liquids and gases collide more frequently, and therefore we prefer to use liquid. Although you can use others as well. There's no restriction of that sort, but just for a preference sake, we use concentrated sulfuric acid. Now, the gas is dried and we collect it in a gas ring. Now, some student asks, "What is this?" This is just a connector. You can show it or you cannot show it. It's up to you. Now, we move on to the more important stuff now. What if they ask us to calculate the moles of oxygen produced? If you don't know O level moles right now, you don't need to worry about this. We'll be talking about it in detail in the moles chapter. However, if you do know, then you might remember the formula that volume is equals to moles into 24 dmq. Now, usually the gas range gives us volume in cm3, therefore we use 24,000 instead of 24. Alright. Now, what if they are asked to calculate the moles of nitrogen dioxide? What will I do then? So first I'll find the mass of the whole apparatus. Alright. I'll find the mass of this part containing of the flask containing water. And after whole of the reaction is over, I'll reweigh it. And when I reweigh it, what I'll notice is that the mass has increased. Why has it increased? Because nitrogen dioxide is dissolved inside of it. Now, I can calculate the increase in mass by subtracting it from the initial mass. When I do that, I have the mass of nitrogen dioxide dissolved. Now, if I have the mass, you can use the formula mole equals to mass divided by mR, and therefore I can calculate the moles. Now, same is the case for moles of calcium oxide. Now, in that case of moles of calcium oxide, what I'll do is that I'll weigh the boiling tube before actually heating it. And after the reaction is over, I'll reweigh it. Because the only thing left would be calcium oxide. No, first of all, let me rephrase my words. I'll actually calculate the mass of an empty boiling tube. Alright? After I have calculated the mass of an empty boiling tube, I'll calculate the mass. I'll calculate the mass after the reaction is over. Now I'll subtract both the masses to get the mass of calcium oxide present inside of the boiling tube. And when I have the mass of calcium oxide in the boiling tube, I can divide it by mR of calcium oxide and get its moles. This is a very important concept that you need to be aware of. Next, there is an example I have done for you guys of what if we are asked to collect a pure dry sample of hydrogen from a mixture of ammonia, sulfur dioxide, and hydrogen. So, this is actually not drawn quite right. Let me actually redo it. So, let's just say that we were given the sample. You don't need to know where the sample came from. So, what I do is actually I pass the mixture from here. Now, when I pass ammonia plus sulfur dioxide plus hydrogen from dilute sulfuric acid, hydrogen won't react. It's a neutral gas. Sulfur dioxide won't react. It's also acidic. However, ammonia, it will react and it will get dissolved. So yes, ammonia will get dissolved. Now I'll have sulfur dioxide as well as hydrogen. Now I'll pass both of these gases through dilute NaOH or sodium hydroxide. Now hydrogen again won't react, but sulfur dioxide being acidic will react with the base, leaving only hydrogen there. Now hydrogen is damp, it's wet, it's not dry. So what I'll do is I'll pass it through anhydrous calcium oxide and then I'll collect it through a gas ring. Now some student might say that can I collect it in let's say through upward delivery? Of course you can, but I don't prefer it because gas range is the most effective method. It's the most efficient method. Alright. Now the last topic we have to do for today in what if we have a metal plus acid. Now we learn this reaction when we move forward, but when metals react with acids, they form a salt plus hydrogen gas. Alright? So, what will be the apparatus that I'll use for it? So, this is a tap funnel. What I'll do is that I'll put the calcium inside of the flask, and let's say I'm using a reaction between calcium and HCl. Alright? So I'll put the calcium inside the flask, alright? Then I'll close the tap funnel. I'll fill it with the acid I then open the tap funnel, the acid drops inside the the flask, the calcium reacts with the acid, hydrogen is released, it is then collected in a gas syringe. However, this method is not very effective because some gas might get trapped here. Let's just say here. So I don't want you guys to use this method. Instead, the other thing we can use is that we attach a string to, let's say, a small test tube, and we have calcium metal inside of it. I fill, I pre-fill the beaker with acid and close the apparatus. After closing the apparatus, I pull the string. Pulling the string will make the calcium fall. When the calcium falls, it will react with the acid. It will react with the acid to give hydrogen gas, and hydrogen gas is collected. It's actually brilliant and amazing. Alright, now you guys might have a question that why can't we do it like something that, let's just say, this is the beaker, this is the flask, you add the calcium, you add the acid, you close it, and you collect the gas. Well, think about it for a moment. In a lab situation, how will you add calcium simultaneously with the acid and close the system all at once? That isn't actually possible. You lose quite an amount of gas in the whole process. So that's why we don't do it. That's why this is wrong. And some students might say that instead of tap funnel, why remember a new apparatus? Let's just use a burette. Now think about it. The mouth of the burette is at the end. Now if I draw it, it would be something like this. How will you how will you actually open the tap? That's not possible again. So you need to be smart about these things, and that will actually help you a lot. So yes, these both settings are wrong and these two are correct. Alright. So yeah, that's about it for the chapter of experimental techniques. I tried to make this video interesting, and I'm sorry for not uploading for quite a while. But let's just say that science is amazing and end with a note that will be future learners. Alright, guys.